Right, hello lovely grade 11s. I'm going to discuss using complementary angles in a general solution. So in order to discuss these specific type of general solution sums, we first have to compare the following two problems. In the first problem it says 5 sine theta is equal to 2 cos theta. And in the second problem it says cos of theta plus 35 is equal to the sine of 3 theta. Now what you need to notice with these two problems, very, very important, is the following. They have certain similarities. Like for instance, both of them have sine function and a cos function, sine function and a cos function. But they have certain things that are very, very, very different, which leads to two completely different methods of solving these two equations. So what makes them so incredibly different is the following. The angles. If you look at the angles of this particular sum, you've got theta and theta. So two different trig functions, sine and cos, but the angles are identical. Whereas in this problem, we have the two different functions, but the angles are completely different from each other. So this one says theta plus 35, and this one says 3 theta. Not the same thing. So let's write that down. Same angles. Very important to notice that. This one has two different angles. Now, Mrs. Prinsloo has actually done this type with you before. So you should be looking at this going, hang on a minute, I recognize these. And these specifically are the ones where you use the tan identity. But specifically, you use it in the following order, where you say sine of theta over cos of theta is equal to tan of theta. So what we will be doing is we will take sine of theta, we'll divide it by cos of theta, and change it to tan of theta. But please remember, what you do on the left-hand side, you need to do on the right-hand side. So let's quickly look at this one first, finish this one up, and then we can look at this one, and then I can explain to you why this method will not work with this particular problem. So with this one, we are going to divide both sides by cos of theta. So over here, sine of theta over cos of theta gives you tan of theta. So this will be 5 tan of theta. And there, cos of theta divides into cos of theta, so I have 2 left. So I'm just quickly going to divide both sides by 5 so that I have tan of theta is equal to 2 over 5. Now, from here on, it's incredibly easy to finish because you can find your reference angle by putting that ratio 2 over 5 into the inverse tan. So that will give me my reference angle on my calculator. So I'll go shift, inverse tan of 2 over 5, and it gives me a reference angle of 21,8 degrees. And I can then put that into the general solution for tan. So the general solution for tan just says theta is equal to the reference angle of 21,8 degrees plus k times 180, remembering somewhere on the page to mention that k is an element of the integers, so you don't get penalized for forgetting about that. So this is something Mrs. Prinsloo has done with you before, pretty easy and straightforward, only allowed if the angles are the same. Now the reason it's only allowed if the angles are the same is if I put the sine of theta over the cos of alpha, for instance, that is never going to be equal to the tan of theta. To be able to use this identity, this one, please note the angles must be the same. So the moment we get to this problem, you should realize because the angles are not the same, there's no way you can change this specifically into tan of anything other than 3 theta. So if I go and I divide this side, I have to divide it by the cos of 3 theta to get the tan of 3 theta. But what I do on the one side, I do on the other side. And if you divide that by the cos of 3 theta, it goes absolutely nowhere. You can't simplify it. So then you're completely stuck. So I'll show you what I'm talking about. So this is wrong, by the way. Don't do this. This is wrong. If you go and you say, I take the cos of theta plus 35 degrees equal to the sine of 3 theta, and then I divide this side by the cos of 3 theta, I have to divide this side by exactly the same thing, which is the cos of 3 theta. And then hopefully you should see this will change into the tan of 3 theta, sure, but this goes absolutely nowhere. And that is why you do not want to do this, because it does not give you a solution to the question. What we are going to be using here is we're going to be using one of our reduction formulas. But we always seem to forget that in my reduction formulas, I have something called the complementary angles. The complementary angles. So if I use 90 degrees minus a particular angle, then what happens is the following. So I'm just going to show this to you, just so I can jog your memory. If I have the sine of theta, I'm allowed to change theta into the complementary angle 90 degrees minus theta if and only if, so listen very carefully, if and only if I change sine into its complementary function, which is cosine. Now, this might seem a little bit strange to you guys going this way, but if I was going from this step to that step, that would actually be very easy to do. Most of you guys, if I gave you simplify the cos of 90 degrees minus theta, would tell me, oh, 90 minus theta means cos turns into sine. But if you can use it this way in mathematics, you can definitely use it the opposite way. So we are going to go and we are going to use complementary angles so that I can use complementary functions. And you'll see just now how it solves my problem. Okay. So going specifically to this one. I'm now going to go and I'm going to say, and by the way, you can pick which side you want to do this to. I generally pick the one with sine in it. We'll do an example just now where it's probably not a good idea to pick the side with sine in it, but I'm going to pick the side with sine in it, and you'll see just now why it's not a bad idea to do it. Probably I think the reason I do it is because I think cosine has an easier general solution than sine. Okay, so what I'm saying is the following. I'm not going to touch this side at all. That's going to stay the cos of theta plus 35 degrees. But on this side, I'm going to change 3 theta into its complementary angle, which is 90 degrees minus 3 theta. For those of you guys that have forgotten what complementary angles are if you add two angles and they add up to 90 degrees, we call it a complementary angle. So therefore 90 minus this angle is the complementary angle of that one, because if you add them together, it adds up to 90. But the rule in trigonometry says very clearly, if you change an angle into its complementary angle, you have to change the function into its complementary function. And for those of you who don't know this, the complementary function of sine is cosine. Now, hopefully you guys will see how useful this is. The reason it's so useful is before I had cosine on the left and sine on the right with different angles. Now at least I have the same function on both sides. I have cosine on the left and I have cosine on the right. And because of something called the principle of equality or equivalence. So the principle of equivalence in mathematics, a very fancy schmancy word, but what it pretty much says is it says, if the functions are the same, but the left-hand side is equal to the right-hand side, then logically speaking, the angles must be the same. So we can actually drop the cosine functions and equate the angles. And this is pretty much the only tricky thing about this process, is the moment you go and you drop that cosine function and you equate the angles, one of these two angles must be treated like the reference angle. And it's your choice. You can pick which one you want to make the reference angle. So I'm going to go and say, this side, right there, that's going to serve as my reference angle. And because this is going to serve as my reference angle, I'm going to treat it exactly like all reference angles when I substitute it into my general solution. So I start by saying theta plus 35 degrees, dropping that cosine function, is equal to, and please remember, your sine general solution as well as your cosine general solution always have two parts to it. So this will be the first part to it. So in the first part of your cosine general solution, remember you take the reference angle just the way it is. I don't change anything to it. So I just write down that 90 degrees minus 3 theta, which is my reference angle, and then please remember over there, plus k times 360. And somewhere on the page, I write k as an element of the integers. And I'm going to leave this now just for a second so I can write the second bit down. I'll come back to this just now. So the second bit of that cosine general solution is then the only tricky part here. We're going to go and say theta plus 35 degrees is equal to, and hopefully you guys will remember, the general solution for cosine says you use the reference angle as it is, right there, so you can see, but then you also have to put a minus in front of the reference angle for the second part. And because this is a polynomial, meaning it's got two terms, I have to put a bracket around it. So I have to put minus the reference angle. And in this case, the reference angle is that 90 degrees minus 3 theta. And then the rest of the general solution plus k times 360. You don't really have to put the k element of integers again because I've put it over there. So now that I've written down the two parts of this general solution, all that needs to be done now is it needs to be simplified algebraically. So algebraically, we're going to put all the variables on the same side, meaning I'm going to say theta plus 3 theta is equal to 90 minus 35. Plus k times 360. So I simplify and I say theta plus 3 theta is 4 theta. 90 minus 35 is going to be equal to 55 degrees plus k times 360. And then please remember, when I divide by 4 over here, I have to divide all my terms by 4. This one, and that one. So 4 theta divided by 4 is theta. Now 55 divided by 4 is equal to 13,75, or if I round it off to one decimal place, it's going to be 13,8. And also remember, this is very easy to forget, so please don't forget 360 must also be divided by 4, so that's going to be k times 90 degrees. So that is then the first part of my general solution. The second part of my general solution, like I said, remember we use positive or the reference angle as is, and then we use the reference angle with a negative in front. So please remember, people, I've got to distribute that negative. So theta plus 35 degrees is minus 90 degrees plus 3 theta plus k times 360. And then I can just again do what I did with the previous one. Careful now, theta minus 3 theta is minus 2 theta. Minus 90 minus 35 is then going to be equal to minus 125 plus k times 360. And then just to finish it up, I'm going to divide by negative 2, but please remember every single term must be divided by negative 2. So that divided by negative 2 is theta, that divided by negative 2, so minus 125 divided by negative 2 is then going to be equal to 62,5. So 62,5 degrees. And then even this one has got to be divided by negative 2. Now, by the way, if you go and you say a positive divided by a negative is a negative, it really doesn't matter whether k has got a positive in front of it or a negative, because k is an element of the integers. So it really doesn't matter. If you accidentally go and you write the plus again, that also doesn't matter. But just algebraically, because I divide a positive by a negative, I'm changing it to a negative. And then 360 divided by 2 is then going to be 180 degrees. And that is then the two parts of this particular general solution. Now I want to do one more example just to show you that sometimes it's a good idea not to change both of the functions to cos. Sometimes it's a better idea to change both of the functions to sine. So if you look at this one, determine the general solution of sine of 2 theta minus 10 degrees equal to cos of theta. If I wanted to change this one to cosine, I need to change this one to 90 degrees minus. but then it would look like this. With the bracket, please, because if you don't put the bracket in front of it, it's wrong. So listen carefully. If you have a polynomial in your angle, so more than one term in your angle, and you want to change that into the complementary angle, you have to go 90 degrees minus bracket, and then everything there needs to be written over there in order to do that cos of theta. Now, by the way, if you've gone to the effort and you've gone to the trouble of doing this, it really doesn't matter if you continue. So you can go ahead and you can do this one just like the previous example. But maybe, just maybe, this one would have been easier if I did it like this. Change that one into a complementary angle and a complementary function. So this will be sine of 2 theta minus 10 degrees is then equal to changing theta into the complementary angle, which is 90 degrees minus theta, and then I get to change cosine into its complementary function, which is sine. So this might actually be a better or an easier way to do it. But now comes your problem. The moment I realize my functions are the same, I'm going to drop it. One of these two needs to serve as the reference angle. I generally just take the right-hand side as the reference angle. It really doesn't matter, but I just find it's a little bit easier this way. Now, I have to now go and I have to use that reference angle, but I have to use it in the sine general solution. So remember, we have two parts to our sine general solution as well. So the first part to our sine general solution says that 2 theta minus 10 degrees is going to be equal to that reference angle as it is. So 90 degrees minus theta plus k times 360. And again, just somewhere on the page, please do not forget k is an element of the integers. And I'll come and I'll simplify this just now. The second part of my general solution for sine, however, is a little bit more tricky. Because remember, it's 180 degrees minus my reference angle. So again, 180 degrees minus my reference angle, but in this case, my reference angle is that 90 degrees minus theta. So I have to write all of that down, again, people, in brackets. Because the moment you subtract a polynomial, you have to remember to distribute. And then we'll just put the k times 360. So now I've set up the two parts of my general solution, so that all that needs to be done now, it needs to be simplified algebraically. So I say 2 theta plus theta is 3 theta. 90 plus 10 is 100 degrees, plus k times 360. And then I just have to divide every single term by 3. So 3 theta divided by 3 is theta. 100 divided by 3 is going to be 33,3, if I'm not mistaken. Let's just double check. Yep, 33,3 if I round it to one decimal place. And please remember to also divide 360 by 3, which means it's k times 120. And then to finish this one up, please remember we need to distribute. So it's 2 theta minus 10 degrees is 180 minus 90 degrees minus gives me plus theta, plus k times 360. So then I can go 2 theta minus theta is theta. 180 minus 90 is 90, but 90 plus 10 is 100 degrees, plus k times 360. And then I'm done with the general solution for this particular one. And this is then specifically if you have a sine function and a cosine function on opposite sides of the equal sign, over here, but the angles are not the same. So I cannot use the tan function identity. I have to use my complementary angles. Complementary angles, complementary functions. So that's it. Thank you very much.